Hi everyone, in this video I would like to revisit a problem that I have solved before but it is not optimized. So this time we'll try to optimize it. And before I made this video, I have spent some time to think through the problem again, and I kind of have some idea now that I would like to try out. So again, this is problem 230, k smallest element in PST. Alright, so I'd like to go back to our observation. So this is based on the fact that, first of all, let me just, how am I gonna do this? Okay, so you can ignore this part. Okay, so observation, and here I'm gonna put my findings. One is that for the Inorder, is it Inorder or Preorder? Okay, Inorder. So Inorder, so if we look at the Inorder of a given subtree, a given binary tree, we will observe that anything that comes, okay, let's look at just one example there. So let me write down the naming of the examples. So in the problem we have examples 1, examples 2, and let me call this example 3, then this is 4, 5, 6, 7, 8. So in order, we see that given a root in the preorder, okay, so first item in preorder is root 2. Every node before root in order is in left subtree, and every node after root in the Inorder is in the right subtree. So based on this observation, we could tell if there is left subtree, then second item in preorder is root of left subtree. Okay, and also if there is right subtree, then third item is the root of the right subtree. Okay, so I think based on this, we could build the tree recursively, but we need to keep in mind that it has to be bounded. So for example, if we look at, let's see which are a good example here. Okay, how about this? Inorder is bounded by the by all the parents. Okay, let me put down an example here. So examples 9, we have 1, 2, 3, 4. In order, it would be 1, 2, 4, 3. I mean, pre-order, it would be 1, 2, 4, 3. Then in order, it would be 2, 3, 1, 4. So in here, we see that 3 is bounded by 1 and 2. Okay. And we cannot just say that everything after 2 is the right subtree of 2. 3, 1, 4 is subtree of 2. Wrong. So this is wrong. This is right. 3 is subtree of 2. Then we can say 4 is not subtree of 2 because parent of 2 is 1. Okay, so I think that should work. Now I would like to go through some examples that we have come up with here. So the first one, we have first example, we have 3, 9, 20, 15, and 7. So we put in 3 there, and then we see that is a left subtree. So we put in 9, and then we put in 20, because that is also a right subtree. And then in the 9, we see that there is no element on the left side. So there is no more left subtree. And then between 9 and 3, there is no item. So 9 has no right subtree. And then we move on to 20. Before 20 and 3, there is 15. So that is left subtree. So we put in 15 there. And then finally the 7. Second example is just one node, so -1. Third example here, we have 1, 2, 4, 3. So we put in 1, put in 2, put in 4, and then put in the 3. So I think this works for all our examples. Now I would like to move on to coding this solution. So here in our questions, we are given a function build tree, and then the list is preorder and inorder. So I would like to further optimize it by using the I'm gonna call it index. So IDX is a dictionary, and then in here I'm gonna store the the index of each of the nodes. So for I, x in enumerate the inorder, idx of x equals I. Okay, so we are gonna use this index dictionary to tell whether there is an element on the left child or the right child. Okay, so we begin by creating the root node. So what we need to do here is let's see. So we put in the left and then put in the right. Okay, I'm gonna turn the preorder into a stack. I'm sorry, put it into a deck. So DQ. So preorder equals DQ of preorder. Then gonna call, let's see, actually I might need to do it recursively to do it easily. Let's see. So if I create a function, because I need to know where the bound of the current node is, right? I don't want to keep on tracing the parents. So let's see, if I define a function, then I would like to store the left and the right boundary. And then I'm gonna call the preorder repeatedly. Okay, so if we use a while loop, right, I cannot use a while loop. So, alright, let's do it this way. I'm gonna call a function, and then it will pass in the left and right pointer. Let me think about it for a moment. So we are gonna do it level by level. Okay. So first of all, I'm gonna create the root, which is 3 node of preorder dot pop left. Okay. So current level, there is only root. Now what I'm gonna do is, okay, I think I can use a recursive, I mean iterative, but isn't it much more troublesome to keep track of all the boundaries? Yeah, I think I better use a recursive way instead. So I'm gonna define, let's see what we need here. I'm trying to come up with a way that is much more clean. How are we gonna do this? Okay, let's see. We need to keep track of all the boundaries. So how am I gonna do that? Alright, I think I don't need to check whether I don't think I need the index here. Sorry, let me just cross out everything for now. Because like in our first example, if we have a, let's see, a pre-order is 3, 9, 20, 15, 7, 9, 3, 15, 20, and 7. So if we first build, it's called a visited set. So we first have 3, and then 3 has 9 there, and then the right hand side is also not found yet, so we add the 20. 9 and 20 is same. Now 9, the left of 9 is nothing, so there is no type. While for 20 there is 15 which we have not seen, so we add a type there. And then 15 we have seen. Now the right of 20, there is something, so put in there. Yeah, I think we don't. Oh, actually, it is much more efficient if we have the index. So let me keep that. So index is dict for I, x in enumerate in order. Index of x equals I. Then what I'm gonna do is that I'm gonna look through the preorder for x in. Actually, I don't think I can do it this way. Let's see. Okay, I'm gonna use a while loop instead. So while actually I think we need to start with the root. So see if I create a root, this would be the 3 nodes. Oh, okay, let me just redo what I did before. So preorder equals dq of preorder 3 node dot preorder dot top left. So now I'm gonna check while preorder also I need to store the current level. Current level equals dq of root. So while preorder let's see how we can do this. Okay, let's just use the current level instead. So while current level, then for node in current level, if the preorder is empty, then we just exit. Okay, we return. Sorry, we don't need to do that. Let's just ignore that. I think because see preorder because we can always check before we pop it. So let's just move on with this. Alright, don't forget the visited set. Visited equals root dot file. Okay. Now let's see. So we are gonna check if on the left side there is unvisited. Can it be possible that we have visited the previous node? Okay, I think there's no way because the pre-order is we visit the left and then we visit itself. So everything on the left is not visited yet. Then it means the, okay, let's do this. If the in order of index of the current node dot fall -1, and this is not in visited, then we are gonna pop it. Sorry, visited has to be a root. I mean, oh no, sorry, it has to be the file. So we pop the value in order dot pop, and then we set the left node dot left equals 3 node of 5 visited dot add the file and then don't forget the next level, the append the node dot left. Okay, and then we do the same for the right, and then so on and so on. We can return the root. Is that? I think this could work. Let me quickly walk through the code again. First of all, I check the index of the current of the value in the Inorder so that I can quickly position the quickly tell the position of the node in the Inorder list. And then I'm gonna create the binary tree level by level. I will start at the root node, and that will be the level 0, which has the root node itself. And therefore, each of the node in the level, I'm gonna check whether there is an unvisited node in the Inorder. If so, then I'm gonna create the left chart, and then I also check whether there is a value that is not explored yet on the right side. Okay, and then once I do that, I'm gonna keep on building the left and then the right, and so on and so on, until at the end I will have created all the nodes, and thus I got all the full tree. Okay, now let me quickly go through the examples again there. In the first example, okay, let's just go through it properly. So for example, I'm not gonna go through all the examples, but I'm gonna handpick some of the good ones. So first examples, we have 3, 9, 20, 15, 7, 9, 3, 15, 27. So first of all, we have the root node 3, and then we mark it as visited. Then the left there is 9. 9 is not visited, so we create 9. And then we have 20. We also check the right side. There is 15, which is not explored yet. So we add there 20. And then for the 9, we check the left side. There is nothing there. The right side also has nothing. For 20, the left side has 15. So there must be a left chart. We add the 15 there, and then the second. So first example, we got it correct. Now let's see the 9 example. The 9 examples, we have 1, 2, 4, 3, and 2, 3, 1, 4. First of all, we create the 1, shifted 1, and then there is left chart there. Also there is right chart. And then 2, there is nothing on the left, but there is something on the right, so we create 3. And we have nothing else to build on. Seems correct. Now I would like to go to example 3. We have 1, 2, 4, 3, and 3, 2, 1, 4. So we build 1. There is something on the left. There is something on the right. Now, is there something on the left of 2? Yes, there is 3, and thus we got it correct. Now let's look at the examples 8, then this is interesting. We have 1, 2, 3, 4, and 3, 2, 4, 1. So we visit 1. There is something on the left, nothing on the right. There is something on the left of 2, something on the right. Okay, I think I am pretty good about this. Let me put the code into LeetCode and try to run it. Hopefully we got this better optimizations. So in here this would take like ON at most, because ON, and therefore each node I'm gonna check the left and right. So that will be like O to N with this, which is still ON. And because we are using set there, or we set it in, it is quite efficient. So let me try this up. Call it index equals dict. I comma for in order index of all equals I. Preorder, we turn it into a deck. Okay. Now the rule is gonna be we pop one of them for equals preorder dot pop. Is it pop left? I think so. 3 node of 4 file, and then kernel level is gonna attack and we also need the next level. Level is deck, and then deck. This would be the root. Actually, we could just use a for loop there, so we can just let's just call it level. So get then while level for in range length of level, I'm gonna pop not equals level dot pop left. Pop left. And then I'm gonna check if in order. Okay, I forgot the visited set. Visited equals set of 4. Okay. If in order of index of node dot fall -1 in visited, not in visited. Here I'm gonna check first if there is anything on the pre-order. If not pre-order, then we just continue. Or I think we could just let's see. We can just directly return it, right? From the root. Okay. So in here, for equals preorder dot top left not dot left equals 3 not of value. Now we need to visit the file. Visit add the file. Then we create the left, and then we append the left node. So left row dot append node dot left. Okay, now we do the right hand side. +1 not visited. Okay, don't forget to check out our boundary. If this +1, it has to be cannot be less than 0, because otherwise we overrun the size. And same for the size here. Now this has to be less than the length of Inorder. Okay. Now here we are setting the right, and this is also setting the right. Okay, I think this works. Let me try to run it. I might get an error here. Yep. Can uncat. Okay, so for here it has to be enumerated. Set and key object is not iterable. Okay. Then create a list. Actually, I think it's tidier if we just do it separately. Preorder.add form. Okay, what is it containing now? The queue of root. And again, I like to separate it. Level dot append connection dot append. Okay, we miss a T there. This one is wrong. Expected empty. forward this will print out, return the root. It's taking too long here. Okay, when I try to submit it, I think it's a bit slow. I'm not sure why. I think it's ON here. Okay, we got a wrong answer. So we are missing the 4. What we did is just 3, 1, 2. Then we are missing the 4. Okay. How did we miss that? Let's use the test case there. 3, 1, 2, 4. Okay, so let's do some debugging. Clean up the level. Initially that is 3. And then we have 3, 1, 2. Oh, I think I got it wrong here. So 3, 1, 2. 2 is 1, 2, 3. 3, 1, 2, 4. How come the pre-order is 3, 1, 2, 4? Oh my god, I misunderstand the question again here. So pre-order is, I was expecting it would be 3, 1, 4, 2, but it is not the case. And instead it is 3, 1, 2, 4. Gosh, I am wrong this whole time. Okay, so preorder is printing the parent. Alright, so actually the preorder that I was thinking is a like I said, it's a PFS of the tree, so I was wrong. Sorry, I think we are gonna stop the video here and then I will redo this in another attempt. Thank you.